Hello everyone. So today we are going to continue with the series of lectures on work energy and power. So in the last class we learned about conservative and non-conservative forces and their work done, and followed by we also learned about what is conservation of mechanical energy and under what conditions we can actually conserve mechanical energy. Today our topic would be analyzing vertical circular motion. So we have a basic idea about circular motion on horizontal plane. Today we are going to look at the dynamical approach of circular motion, but in the vertical plane. So let us begin with the session now. Now I'll begin. Yes. So vertical circular motion. Vertical circular motion. First of all, we need to understand what are the constraints given on the mass for vertical circular motion. Let's take a scenario where I'm tidying up a mass m with a string and it's been whirled around in this way. Let's say the length of the string is L. So the radius of the circle becomes L. Now, what all things we have to discuss? See, the very first thing comes in our mind when we talk about vertical circular motion, this kind of scenarios, is that how much is the minimum velocity required at this bottommost point so that it completes the circle. It should not leave the circle in between. So for that, we would be taking care of few things like under what scenarios can it fall? So one of the scenario is if I give it a decent speed, it will move. But if its speed becomes zero in between, then again it will come back along the same path. Maybe it is possible because of the presence of tension. And yeah, so that can be one of the case. The another case would be still if this particle has to leave the trajectory, then the necessary condition would be the tension would become zero without velocity being non-zero, which means for this object to continuously revolve around about this center, it should be having such a velocity and such under such conditions that the tension should not become zero. So that is the necessary condition for VCM to exist. For VCM to exist, the important point is tension at all points should be non-zero. This is the important part. Tension at all points should be non-zero. So let's begin with finding tension at any general point first. So if I'll take this particle somewhere here, so at an angle, let's say theta, what are the forces acting on this mass? So definitely there would be m into g. There would be tension in the string. Okay, and yeah, we also know this angle is going to be theta. So I'll just make a diagram of this. So let's say while the particle was passing through this point P, it was having a speed Vp. So here I can just draw the free body once again. So this is point P. This is the line along which the tension is acting. This is the line. And mg is acting vertically downward. Yeah. And this is going to be theta. Let us discuss everything with respect to the point P. So we would be analyzing it with respect to a non-inertial frame, which means there has to be a pseudo force coming into account. Okay. So if this is the tension, I can break down this mg into two components. That is, one would be mg cos of theta. Here this would be mg sine of theta. Definitely it would be retarding in this direction because of this acceleration g sine theta, okay, which is acting against this Vp, okay. Now, if you look at the scenarios along this line, along this axis, you will find that the mass has to remain in rest. Now, what are the scenarios under which the mass can remain at rest? So there is two forces acting on the outward side. One is this mg cos theta, and the other one is mvp square by r, or let's say L. Okay, it will be mvp square by L. Now, this is the centrifugal part. This is the centrifugal force which the particle would be experiencing. And yeah, so this is the pseudo force basically. Now, these two forces are there on the outward side. Now, which force is going to balance it then? It's going to be the tension. So, tension ka formula, we are going to get it as mg cos theta plus mvp square by L. This is going to be the tension at any point P. Now, if I think about by giving what velocity I can make this a confirm point, then I would see for that particular thing that what should be the minimum velocity given at point A so that it makes a complete circle in the vertical plane. Okay. Similarly, we'll choose a point here. Let's name this point as B. You can also name another point exactly on the top of it, call it C. And something similarly, you can even deal with point D, but anyways, point D and point B would be along the same line of thought. So you can just find the equivalent speeds along the same line. Okay. Now, my question is, what should be the minimum velocity at A provided so that it completes the circle? Similarly, we have to also find minimum velocity required to start the motion from point B, and same goes with point C. Now, if I talk about this particular equation, you will find a very interesting thing, that is, this tension would never become zero. Like, tension cannot be zero if it is in this zone. Yeah, think about it. Like, for this specific cos theta k values, you would never get tension to be zero. Okay. Now then, in which state can it be possible to get the tension zero? Definitely in this zone. So if it is in this zone, the highest possibility, highest probability of tension becoming zero could be this point, because this is the point where the tension would be minimum. Okay. So if I have to show it, what would be the tension at point C, I can find it. So tension at point C, how will you find it? It is going to be mg cos of, okay, by the way, for point C, what would be theta? It would be 180. So theta would be 180 plus m vp square by L. Now this is nothing but m, no, sorry, my bad. It should be vc square by L, because we are talking about the speed at location C. Okay, so it's mvc square by L minus mg, cos 180 is minus 1. So this is the tension, and this is the minimum tension possible in all over the circle. Okay, so we know this is the minimum tension. This is the minimum tension. If they ask you to find the position where the tension would be minimum, it would be nothing but C. Now, the possibility of tension becoming zero is also this, because it is the minimum tension which can be possible. Okay. So if I make sure that somehow I will make sure that tension at point C is greater than or equal to zero. if I make sure this thing, ki tension at point C is greater than or equal to 0, I can definitely say the particle will continue in vertical circular motion. Yeah, we can say this. Okay, the particle will continue in vertical circular motion. So if this is the thing, then can I say uh, mvc square by L should be greater than or equal to m into g? Yeah, you can do it. So in the same way, can I also say vc square should be greater than or equal to g, L into g or g into L? Which means vc should be greater than or equal to under root gl, which means the necessary, or let's say the minimum velocity or speed at point C required would be exactly equals to under root gl. And if you give more than that, then it's fine. But for this specific value of speed at this location, it can just barely cross the circle and it will perform the circular motion. Okay. But if the speed is less than this at this location C, then it can definitely fall down. Yeah. So to make sure if it is not falling, it is continuing the circle, then I'll have to make sure that the speed at that topmost point should be at least equals to under root GL. Now, if we know about the minimum speed required at this location, then can we also find the speed required at this location in order to get the speed here? So yes. So how we will be finding? For that, we have conservation of mechanical energy. Conservation of mechanical energy. First thing, what all forces are acting here? There is gravity, there is tension. Yeah. And let's say if I'm dealing it with respect to ground frame for not getting attached with this centrifugal force. Okay. But anyways, it won't make sense because it won't make any significant change in the final result, because centripetal force or centrifugal force would not contribute in work because the displacement is tangential to the path. So that is the reason forces are perpendicular. So its work done would definitely be zero, right? So what all forces I can say? There is tension, there is gravity, yeah. And if you want, you can say centripetal or centrifugal, depending on your frame of reference. Centrifugal. So interestingly, work done by tension would be zero because tension is also acting in the same way. Like this is the tension and this is the direction. So tension is actually perpendicular to ds. So if tension is perpendicular to ds, work done by tension is zero. Similarly, work done by centripetal force or centrifugal force would also be zero because it is also going to act along the same route. Okay. We know that centripetal force and centrifugal forces are acting along the radius, and we already know that radius is perpendicular to the tangent of a circle. So that is the reason you'll again get the work done of centripetal or centrifugal or CF to be zero. Now what remains is the gravity, and gravity is a conservative force. So I can write work done by gravity as negative change in potential energy of gravity. Okay. So now all of these conditions when they are given, and if I'm asking, is there any non-conservative work done been done? So answer is no. There's no non-conservative forces are present, and there's no work done by non-conservative forces. And we know if there is no non-conservative forces are present, then I can say total mechanical energy at any level would remain constant. So I can also write this total mechanical energy to be constant for two levels. That is, total mechanical energy at A would be same as total mechanical energy at point C. Okay, so if this is the case, let's say the level A is the potential reference zero level. So I'm taking this as a reference level as zero. So I'm going to measure all the distances from this level. So yeah, so let's come and let's write this thing. So kinetic energy at point A plus potential energy at point A has to be equals to kinetic energy at point C plus potential energy at point C. Now kinetic energy at point A would be half m VA square plus potential energy at point A, we have taken it as 0. Uh, so it will be 0 here equals to kinetic energy at point C is half m VC square plus potential energy at point C. So the height over here is 2r, isn't it? It's the diameter. So it's going to be 2r. So what would be the potential energy? mg into 2r. Okay. So these all things are given. Okay. Now anything which can be cancelled out? Yes, we can take out mass and we can also multiply both sides by 2. So finally we'll get VA square equals to VC square plus 4 mgr. Yep, this would be the thing. Now again, what do we need? We need minimum speed required at point A. So for that, we'll use the minimum speed required at point C plus 4 mgr. So what is the minimum speed required at point C? It is under root gl. So which means it's square plus 4. Achha, so I have cancelled out this mass. There's no mass remaining here. It's just gr. Yeah. So it's just going to be 4g into r. Achha, by the way, here r is nothing but l. Here radius is nothing but l. Okay, we can also write this r as l. So I'll just substitute it here as l. So finally, what we are getting it as gl plus 4gl, which is 5gl. So what is the minimum speed required at point A? It is under root 5gl. It's going to be under root 5gl. Okay, so this is the answer. So at point A, how much minimum speed do we require? Under root 5gl. And at this point C, what is the minimum speed? It's under root gl. Now let's see what is the minimum speed required at point B. At point B, so for finding the answer for point B, what we'll use is again total mechanical energy conservation for point A and for point B. Yeah. And that is half mVA square plus 0. Potential energy at level A, I've taken it as 0, equals to half mVB square plus. Okay, how much is the H here for B? Point B, it's going to be, H is going to be R and radius, or radius is nothing but the L. So you can just simply write it as MGL. So finally, we have this equation VA square equals to VB square plus 2GL. Now we need to find this VB square and this VA square minus 2GL. But do we need exactly VB square or the minimum value of it? So we are in search of minimum value. This should be the minimum value which has to be provided in order to make it become a complete circle. So we'll use VA ka minimum value also here and minus 2GL. Now what is VA? We already found it as root 5GL. So its square would give you 5GL minus 2GL gives you 3GL. Therefore, VB minimum is going to be under root 3GL. These are the most important velocities at 3 points. As the same goes with point D as well, like just the direction would change. This is the speed ka direction, like the velocity ka direction in this direction, and it would be here like this. So for just redraw the whole thing once again. If it is a circle like this, doesn't look like a circle. I'll take a circle from here. Yeah, that's fine. Let's take, let's say this length is L, or in general, if I want to say, it's not necessary that always there would be a string. There can be a question on airplanes that if an airplane is taking a complete circular path in this way on along the vertical axis, what is the normal reaction the person would be getting? So there are different kinds of question we get. We'll discuss a few as well. Okay, but let's say for now to make it generalized, let's say the radius is r, and at this point A, for this to complete a complete circle, so I'll just write VA has to be greater than or equals to under root 5 GR. Similarly, for point B, to call this point as B, it would be directed here, and VB, this condition would be like this, under root 3 GR, and for point C, so if this is a point C, this is the direction, say it is VC, and this has to be greater than under root GL. So if these are the conditions there, so it can definitely perform a circle, okay, in the vertical plane. Now, as I was mentioning, there can be good illustration based on this. So let's take up a example here. So the example is there's a mass. The most common thing is the bucket problem. So there's a bucket filled with water, and this bucket has to be rotated with certain speed so that the water which it has inside it, when it becomes like this, like when it is exactly at the top of it, like this, the water should still remain there. It shouldn't fall. But the question is, why does it happen? So let's talk it with respect to the buckets frame, which is the pseudo-Forska frame. Okay. So if you will analyze the masses and everything, like you will find that there is definitely M into G acting on the water. Let's say mass of the water is M. So M into G definitely it's acting. Now, because of certain speed, it has it here. Don't you think it can also get a centrifugal force? Yeah, we would also need a centrifugal force. Now, if centrifugal force is not enough to balance mg, then mg will definitely, like, the water will splash down. But what if the centrifugal force is equal or greater than mg? Then definitely the water would remain here. Acha, if it is equal, then there won't be any normal reaction also getting out in order to balance it. But if it is greater, then there would also come a normal reaction from the surface of this bucket in order to balance that water. Okay, so it's basically if this point has a velocity, let's say v naught. So if this velocity v naught is greater than or equals to, or let's say greater than for now, root GL, then we'll say the normal reaction is nothing but FCF minus mg. And FCF is nothing but mv naught square by r minus mg. This would give you the normal reaction there. Okay. But if V naught is just equals to root GL, normal reaction won't come there, and the centrifugal force is just enough to balance mg. And so this is case one. Case two, but other case is if V naught is less than under root GL. So what do you think would happen? Here, definitely normal reaction is 0. Okay. And this time mg is dominating over FCF. So water falls down. Okay, water will fall down from here. But the idea, so this is a scenario in which you can actually rotate this bucket, and so definitely it's not possible for us to rotate it from here, isn't it? Like directly rotate it from here. So what we prefer is we would be rotating it from this location. Now, to make sure that it should not fall here, then definitely the velocity should be following this condition that it should be greater than under root 5 gr. And once you have achieved this velocity, you can continuously go on and on, but the water would not fall. Yeah. Yes. So yeah, that is the thing. And even sometimes to give an experience of extra gravitational force, or let's say sense of more gravity, sometimes astronauts do this thing with respect to like centrifugal force. So they get into a chamber, and that chamber is going to rotate with a very, very, very high speed. And because of that, they would be getting a very huge normal reaction, and that normal reaction gives them the sense of their weight. So if it is mg, which they are going to feel it on the surface of Earth while they're standing, whereas there, to get a higher g-force, this normal reaction increases, like it would be more than mg there. Okay, so these are certain things. And even it is possible to have weightlessness condition during this whole circle. So you can take this one to be a weightless condition. Okay. And even this one would be a weightless condition. Anyways, it's a free fall now. Sure. So yes, this is all about vertical circular motion. Let's solve a few questions on this. So very basic question is if a particle is performing vertical circular motion, say the initial speed given here is v naught, and this point is A, and this point is B. Okay, and they have said, and at this point C, the tension has become just 0, but it is still performing the vertical circular motion, because if the tension is just 0, then it is possible that it may get unbalanced at this location. But anyways, because of the decent speed which is present here, okay, its centrifugal force will be just balancing its mg, so you won't need any help of tension to balance it. Okay, so that is the reason it can actually continue, and it will make the circle complete. But the question is, they are asking you about the kinetic energy at point A divided by kinetic energy at point B. So they are asking you about the ratio of the kinetic energies at point A and B. Can we find it? Yes, we can find it. So just by this condition, we got the idea that definitely the speed which is given here is exactly equals to under root g into L. So let's take the length as L, radius as L. And definitely then V naught would be also equals to under root 5gl, which means at point B it would be under root 3gl. Now what they're asking? They're asking us to find the ratio. So kinetic energy at A divided by kinetic energy at B, which is half mVA square divided by half mVB square, which this cancels out. So VA by VB ka whole square, which is root 5gl divided by root 3gl and its whole square. So it's going to be 5 by 3. So kinetic energy at point A divided by kinetic energy at point B. Okay. Yeah, this is one of the question. And you can practice more questions on this particular topic. So yeah, that's it for this part. And in the next class, we'll discuss about collision. Sure. Bye-bye. Take care.